So in this particular video, we have an object being shot up from ground level, and it says that after a time of 6.4 seconds, it passes a height of 23.9 meters. So it wants us to find out its different parts, A, B, C, D, E, and F. Alright, so here I have provided a visual for you. A ball is going to get shot upward, and then it's going to come to a stop and then come back down to where it was launched. Alright, so let's do this. To do part A, it asks you what is the initial speed of the ball. Well, in order to find initial speed of the ball, you have to recognize the information given to you here. Here, in this particular problem, we have a time of 6.4 seconds, and after it has been shot up, it passes this particular height at that time, which is 23.9. So right away, I know that I can use my displacement function in kinematics. I know delta y here is 23.9. I'm looking for VI because that's what the question is looking for. It says initial speed, but really it's looking for the initial velocity. We just don't have to include the direction. Time is given. G we know is negative 9.8 near the surface of the planet. So really, this particular function allows us to complete that task quickly. So as long as you learn how to recognize the information given, this stuff should be pretty straightforward. Okay. So here, I replace delta y with 23.9 because it said so. VI I kept as unknown. My time is 6.4 seconds because it says after 6.4 seconds it reaches a height of 23.9. Here the 1/2 gets carried down. G is negative 9.8 meters per second square. And again, time is 6.4 seconds because it's given to us. As you can see here in this particular second line, the only variable that's unknown is our VI. So all we have to do is crank a little calculator workout and algebra stuff. I simplify the 1/2 negative 9.8 6.4 square, and that should give you a negative value because here's the negative sign. So that'll give you a negative value of about 200.7. Well, here on the left side you have 23.9 meters. Here on the right side you have negative 200.7 meters. And here you have VI times 6.4 seconds. So algebraically, the first thing we have to do is combine like terms. So I would combine the 23.9 and the negative 207 here, 200.7 meters here, because those are like terms. So I'm going to move this negative 200.7 to the left side. So that's going to be adding. So therefore, I can simplify the left side, 23.9, add 200.7. That's going to give us a sum of 224.6. And in here, you notice on the right side, it's just VI times 6.4. So in order to get VI by itself, we just divide both sides by 6.4 seconds. So if we do that correctly, we should get a value of 35.1 meters per second. So notice here, the answer is just 35.1 meters per second because it asks for initial speed. And speed here is a scalar and it has no direction. So it's important that you read problems carefully as you proceed. Alright, let's go ahead and do part B. Part B asks us to find the time taken to reach maximum height. Okay, here I don't know what the maximum height is. I just need to look for time. The reason I'm starting with this average acceleration equation is because, well, I know what acceleration is. Acceleration is just negative 9.8. I don't know what t is, that's what I'm looking for, but what I do know is I do know change in v. So I'm just going to go ahead and manipulate this function to solve for t real quick. In order to solve for t, you need to multiply both sides by t so that t can go in the numerator, but at the same time divide both sides by a to get rid of it. So I would just like to do a little swap here for this function. Delta t from the bottom goes up to the left. A on the top left goes to the bottom right. So this particular function looks like this. Time is equal to the change in velocity over average acceleration. And at the surface of the planet, once again, the acceleration is given to us. So therefore, I broke up delta v into vf minus vi. Average acceleration here I kept the same for now. And here we just plug and chug. But it's important to notice at the peak of the flight, okay, because it says here, find the time taken to reach maximum height. The one thing you have to realize so that you can make these tasks easy is that at the maximum height, the ball must come to a stop. So anytime it says maximum height or ymax, you have to know that VF is equal to 0. This is an important association. So therefore, I'm going to plug in VF is equal to 0 because it has to stop before it changes direction. V is 35.1 that we calculated in part A. and therefore A average is simply negative 9.8 meters per second square. So if you do this correctly on your calculator, 35.1 divided by 9.8 is just 3.58. Okay, so therefore the time that it takes for the ball to go from the launch position all the way up to where it reaches hmax is a time of 3.58 seconds, and this is important to keep track of as we do the other parts. All right, so that's that. So it's not too bad. Okay. Part C asks you to calculate the ball's average speed for the entire trip. So for this one, it asks for average speed. I need to figure out what the distance is. So average speed, by definition, is distance divided by time. Well, if it says the whole entire trip, I need to figure out the distance and the time. We already know the time that it takes to go from bottom to top is 3.58. So therefore, by symmetry, it would take the same amount of time to fall back down. So in the denominator here, I have 3.58 seconds plus another 3.58 seconds. So the first 3.58 seconds is for it to rise, and then the next 3.58 seconds is for it to go from peak all the way back to down to the ground due to symmetry. I don't know what the distance is though, but I can find what the distance is pretty quickly using kinematics. I'm going to start with this equation, vf squared minus vi squared equals 2g delta y. I'm starting with this because I don't have to go through time. Not only that, I know at the peak my vf is 0. Okay, so I'm utilizing kinematics equation that benefits me the quickest, I think. Okay, so therefore to solve for delta y, we can just divide both sides by 2g on both sides. So I'm just going to plug and chug. We know that vf at the peak is 0. I'm circling that with my cursor on the top right of the screen here. Vf at the peak is 0, which implies I can cross out vf squared because that's just 0. Vi we already calculated from part A, which is 35.1. We're going to square that. I carry the negative sign down as usual here. 2g is negative 9.8. So as you can see here, the negative signs will cancel out. Therefore, it leaves us with a vertical displacement of 62.86. So that's how high the ball rises before it comes to a stop. But I'm not done yet. This is just the distance going up. It says round trip. So round trip would imply you need to add the distance up and the distance down. So here in my next work, in the numerator, I have 62.86 meters plus the distance down, which is 62.86, again due to symmetry. The denominator hasn't changed because what I do is I just took the time to go up and I added the same time to account for the whole entire trip. But I do like to point out here, okay, there are folks who do physics and there are folks who are just number crunching. If you haven't realized it yet, all you're doing is you're just multiplying the numerator by 2. So really 62.86 plus 62.86, which is the same as 2 times 62.86, because there's two of the identical numbers. Likewise at the bottom, you have 3.58 plus another 3.58. The other way to write it is just 2 times 3.58. So if you've recognized it, the speed for the round trip is the same as just the speed going up, because the 2 in the front, in the numerator and the denominator cancels out. So therefore, the average speed for the entire trip is just 17.56, which is just the same as the average speed for a single way. Round trip just means you're doubling everything, so therefore it cancels out. Okay, so that's something to keep track of. This is just little tricks that you should recognize. So anytime a problem lands at the same spot or goes right and comes back to the same final position as the initial position, the average speed will always be the same for round trip versus and one way. All right. So let's do part D. Part D. It says, what is the ball's instantaneous velocity at 4.8 seconds? Well, instantaneous velocity here just really asks you to find the final velocity at that moment in time. So here, I just wrote out the function to find final velocity, which is a times t plus vi. But you notice here, instead of a, I just wrote g for acceleration due to gravity. I know the acceleration due to gravity value is a constant negative 9.8. The time here is 4.8. And the initial velocity here is 35.1 as we calculate in part A. So if you simplify this, the first term, negative 9.8 times 4.8 is negative 47.04 about. Give take a little rounding error here. And then the vi that we found, I just carry down. And if we add these two values, we get a value of negative 11.94, which makes sense. Okay. So if you kept up with the other part where it asks you to find the time to go to the peak, well, it took 3.58 seconds to get to the top, okay? And then after 3.58 seconds, you're on your way down. So my answer here makes sense because I know I'm on my way down, so my final velocity has to be at some sort of negative value. All right. The other way to do this particular part, which I like, which I hope you pick up as you watch these videos, is, well, I want to cross VI out because I want to start at the peak. Okay. I want to start at the peak because I know for a fact that if I start at the peak, my initial velocity is 0 because it came to a stop and then it turns around. So therefore, I can cross VI out, which makes my work super quick to do. The only thing that you got to be careful is the time. Based on my screen here, we know VF at the peak is 0. We know it took 3.58 seconds to get to the peak. But this particular part D asks us for the velocity at 4.8 seconds. So I think it just takes a little bit of thinking. Well, 4.8 seconds would put me on my way down. But if at the peak it's already 3.58 seconds, the fall from 3.58 seconds down to 4.8, all you have to do is take the difference in the time. So therefore, my work here for G, I put negative 9.8 because it is. T though is 1.22. The 1.22 comes from taking 4.8 seconds, subtracted from the time it took to get to the peak. So watch my cursor. It takes 3.58 seconds to get here. That is 3.58, and then from 3.58 to 4.8 is another 1.22 seconds, and that's what I'm using. So I like to start at the peak because my VI is 0. So if you simplify this on your calculator, you'll get also a negative value of 11.96. Here, I know in the first value I got a negative 11.94. Here is negative 11.96. The difference of 0.02, that is because there is rounding involved here, but essentially it's the same value if you don't get too technical with the 0.02 difference, okay? So that is the answer as well. All right, let's go ahead and part E. Part E asks you to find the average velocity between 1 to 3 seconds. Well, to find average velocity, you have a couple of choices. For this part E, if I was doing this from scratch, I would do it using this particular function. It's just quick, okay? To find average velocity, I need VF plus VI divided by 2. Well, I can find VF super fast. Well, VF is just G times T plus VI. Here, instead of VF, I just wrote V of T because V of T and VF are the same notation. I know what G is. Here, my time is 1 second. I want to add that to the 35.1 because that's my initial velocity. So I can find the velocity at 1 second super fast, 25.3, okay? Or, literally, you can simply take 35.1 and just subtract 9.8 because on its way up, it slows down by a rate of 9.8, okay? So therefore, this answer makes sense. Now, I already found the velocity at 1 second, which is my VI. The reason I need to find out 1 second is because this particular part E wants us to find the average velocity from 1 second to 3 seconds. So it is important that you pay attention to the interval presented to you and not make false assumptions. I need to find the velocity at 1 because it starts at 1. I need to find the velocity at 3 because it ends at 3. So therefore, I can use the same function again, except I'm going to exercise it for 3 seconds. Well, same function, so G is negative 9.8, except T though, I'm going to put in 3 seconds. My VI hasn't changed because I'm going to go from 0 to 3 seconds. Therefore, the final velocity at 3 seconds is 5.7. It's still on its way up, it just happened to be slowing down. So therefore, I know my two values. So from there, I can just substitute in. My VI at 1 second is 25.3. My final velocity at 3 seconds is 5.7. And then I can just sum those up and divide it by 2. If you do that correctly, you should get a value of positive 15.5. I include the positive sign here because it's just average velocity, and average velocity is a vector, so I need to include the direct sign. So it's a positive change as it moves forward, or the average is a positive average, okay? The other way to do it is simply by using displacement over time. To find average velocity, you need displacement over time. Well, I know my time is 2 seconds. That's easy to do. The difference from 1 to 3 seconds is just 2 seconds. Well, but I don't know what my delta y is. I don't know what my change in position is during this time interval from 1 to 3 seconds. Well, I can use the displacement function. So delta y is VIT plus 1 half gt squared. But this is usually where folks make a mistake because they don't pay attention to the interval that's presented, okay? Here, my VI is actually 25.3 meters per second. You cannot plug in 35.1. The problem didn't start at 0 second, it actually starts at 1 second. So at 1 second, if you kept up the work on the left side here, at 1 second, the velocity has slowed down to a rate of 25.3. So because this problem starts at 1 second, I need to plug in the proper VI, which is 25.3. Here t, well, t is 2 because it went from 1 second to 3 seconds, which is a difference of 2 seconds. So t is 2 seconds. The rest of the work here is pretty no-brainer. 1/2 just gets carried down. G is negative 9.8 because it's given. T is also really given in part E because it says from 1 to 3 seconds. So if you simplify all this, the first term gives you 50.6, and the second term, 1/2 times negative 9.8 times 4, because 2 squared is 4, will give you a negative value. But you're adding a negative, really it's like subtracting a positive. So therefore, if you do this correctly, you should get 31. Well, hopefully by now your brain is on, well, delta y is 31. 31 divided by 2 is 15.5. So I'll just carry my work down here. So wherever delta y is, I'm going to plug in 31 meters because I just found it to be 31 meters. The 2 seconds is because the interval is from 1 to 3. And if you do that correctly, you notice 31 divided by 2 gives you the same 15.5 meters per second. Okay, so that's that. Now, before I do part F though, part F asks you to draw the position time graph and the velocity time graph for round trip. Okay, I'll go ahead and give you the answers here, and then I'll show you using decimals. Well, free fall is pretty easy to do. This is your position time graph because the object has to go up, come to a stop, because the tangent line here at this particular peak is 0, implying that it must come to a stop, and then it changes direction and now it falls back down. So this is a nice, perfect upside down parabola. It's a parabola because the object goes up and comes down, and the only reason it looks like a parabola is because time is increasing, so really you're stretching that motion outward, so it looks like a sat face. Okay, now the velocity time graph is pretty easy to do. Well, the velocity time graph needs to start at some positive value because it's being projected upward. So where my cursor is, if you actually plug in the number, it would be 35.1. Well, I know that throughout the whole entire flight, the acceleration due to gravity is negative, which makes sense because the object starts at some positive value, aka being shot upward. At some point, it starts to slow down. It slows down to some lesser positive value. It slows down to some lesser positive value, and eventually it comes to a stop at this particular time. But once it stops, though, it actually now starts to fall down at the same rate. So it's increasing at the same rate. And what is that rate? Negative 9.8 meters per second squared. So if you notice here, this velocity time graph has a negative slope because from left to right, this is a downward slope. So in physics, at the surface of the planet Earth, this slope would be negative 9.8 meters per second squared. Okay, so I'm going to use decimals here to show you that the two shapes here can be calculated using physics functions. So keep in mind, this is position time graph. The second is a velocity time graph. So I'm going to exit my screen real quick here. Okay. I'm going to go to decimals. Oh, excuse me, decimals. Okay. Now, so if you are keeping up, your position function is VIT plus 1/2 GT squared. Well, my VI is 35.1. My independent variable is X, but in decimals, you got to call it T because in physics, we're graphing with respect to T. I want to add it to 1/2, which is 0.5. Okay. I want to times that by negative 9.8 because that's the acceleration due to gravity, and then I'm going to times it by t squared, or excuse me, in this case, sorry, I have to do x squared. As you see here, I'm used to typing t squared in my calculator, or excuse me, in my presentation. So if you notice here, the graph here will give us a nice parabola. So I'm going to change the x-axis because time cannot be 0. And then I'm just going to change this where I can change the interval here to help you visualize. Let's go like 20 or 50. Okay. So as you can see here, the shape of this graph is a parabola. Okay, so I'm going to zoom out, just make the x-axis. Okay, so as you can see, this graph here is a nice, perfect upside down parabola, which mimics what I just showed you in the presentation. Yeah. Here the graph keeps going because if it was falling past the landing point, it would keep going down. But for this particular problem, it lands at the same spot. So it lands from the ground, therefore it's going to land on the ground. And so therefore the shape is what we're looking at. It's consistent. Now let's plot the velocity time graph. The velocity time graph is plot using velocity function. So verbally, it's Vf is equal to At plus Vi. Well, A in this case is negative 9.8, so I'm just going to use parentheses, negative 9.8, and then T, but instead of T in decimals here, we use X plus Vi, and Vi is 35.1. So as you can see here, if I just move this up a little bit, the graph traces out the same diagonal downward slope that I gave you. Okay, so here the initial value is 35.1. Here's 0. Here's 20. That is about 35.1, and it's going to slow down until it comes to a stop, and then after it stops, it picks up speed in the negative direction. Once again, the slope of this line right here is negative 9.8 because the slope of a velocity time graph is your acceleration. Acceleration due to gravity is negative 9.8, so I need a negative slope based on the shape, and if you actually calculate the values using numbers on the graph, you'll get a negative 9.8. So that's why the shape looks the way it does. Okay, so therefore I should prove to you that y of t and v of t are these two shapes. All right, I hope that helps. Stay nerdy, don't be whack.